All right. Good morning, everyone. Today is our last schedule lecture. Okay. So in this case, if you have any question during the session, since I'm go full online, so don't text. Just turn on your audio and speak. Feel free to interrupt me. Okay. Otherwise, just keep going. So today is the last schedule lecture, but we won't. But I plan to have one more session of lecture next week, same time, 11 o'clock, but really about unit review and exam preparation. So if you're unable to make it at that time, so there's always going to be a recording, okay, a recording of the lecture so that you can view it afterward. Okay. All right. So today here we will actually touch on the component that actually hopefully makes sense to have because we've been dealing with the application design and in terms of interface design component, assignment 2 and 3, and hands-on component. Today is really try to get you into look at some of the technology, okay, that underpin those technology that are available today. So you'll get a sense of hopefully have more understanding of the field, okay, of this area, okay, and then understand how it's about, okay. So the machine side of the virtual interface that we're talking about here, the virtual interface is somewhere in the middle block. Okay, so hopefully you can see my cursor, my mouse cursor. So you can see here. So there's a kind of middle that we have been playing with. So this is a blue box mediations models, the interface that we're talking about. The two sides, one side to the humans on the left-hand side, and then basically try to look at what they actually mean to the world, which is on the other side. Okay, so this machine side are the two major components that currently what we're seeing here, how people see them, that's through the display, and how people control them. So that's what we'll talk about next in the second. So how people display on the top, okay, how they see the feedback from machine, and how they interact with machine. So this is a virtual display. So this is just try to get to understand. Display is not. We might be looking at how it's actually using as a components. Okay, so a display, monitors, and screen, that kind of thing. But one thing that in our area you should be a little bit aware of human factor size of that. So that's human visual channels. Okay, so this is some of the terminology that people are familiar with. Okay, in the luminance, intensity. Okay, so that's dimmer, brighter. For a quick term, contrast, modulations, pixel elements, how the picture, how the pixel, how the display, how the image is formed. So that's a different technology. Spatial frequency, so you might know them at the resolution of your display. Okay. And spectral response, so this is a range of colors and how the vivid your display are, things like that. That's a more common term to use. So that is a range of a spectrum. Okay, so sufficient contrast, sufficient resolution, refresh rates, 60 frames per second, 60 hertz. You might have heard that if it's a monitor is lower than that, then the flicker rate create a flicker image on your screen. So that's usually the old display technology, but with your LCD display technology, this wouldn't be applied to that. Okay. And the term that we have used is called a field of view. So that's basically ability for you, how big the display that can show in front of you. Okay. So generally people were looking at somewhere around closer to 180s for a full field of view display. So right now the the head mount display like Oculus is around 110, so slightly somewhere around that. So that is pretty good. Yeah, so, but as you probably should be familiar now, is the field of view it's not just display itself. It has an instantaneous field of view. For that means is that it's effective. What effective means of field of view means. So that is basically the field of view of the display, the optic itself, the lens in front of you, in the headset, and also the head tracking capability, which we'll talk about in the second half of today's lecture. Okay, which is a combine of both to generate a field of view that expand across the area. So this one is just to give you a sense of visible spectrum. So in the spectrum here go all the way from a short wavelength, long wavelength. So you can see here the color, microwave, radio, radar, X-ray, gammas. The visible light is just a very, to the human eyes, just small in the middle. Okay, a very tiny one. So that's come from the far left, which is ultraviolet, all the way to infrared on the right. Just to give you a sense that sometimes the sensor could go beyond the invisible spectrum, but humans would need, as far as the visible spectrum, it has a limited range that it could work with. Okay. So this is just a good example for luminance. So in this case, you can see here people who has it's the same image, but one is actually more brighter than the other. So if you look at these two images, you should see more details in the other one. Okay, you can compare the scenario like going to the darker rooms, dimmer light, those kind of things. Okay. So the contrast here a bit difference. Okay, this one is a different threshold between the black and white. Okay, how much they can differentiate it. So that you will see the effect in the early LCD display. Okay, so, that maybe 5-10 years ago, they just came out. So you will see that some white, there was a gray when the images has a bit of black in them. Okay, so that is how you see the between very far black and then very far white with a gradient between them. Okay, that is basically provide you with a contrast, the image that we can see. Okay. So the following here will be the image. I'm not sure the effect will be kind of close. Okay, so this is work done by a professor in Japan. Okay, so this is he calls snake, so rotating snake. Okay, the trick here is that, as you know, that this is not a GIF image. This is just a static image. But you will see that if you look at them, you will see some of them are moving, some of them are not moving. Okay, so in this case here is that the trick here is that it play around the idea of your peripheral view. Okay, so that means it's not your core that what you're looking directly, it's the one that you're not focusing on. Okay, so that means is that to counter that effect, if you see anything moving, any circle moving, you just move your eye and focus on that one, and it will stop moving. Okay, I'll give you maybe 10 seconds to play with it. This is not a GIF image again, and you can see that. So this is just to demonstrate the fact that human eyes is actually it has a complex processing that can do, but we also have limitation in them. So it's some artifact would fool our thinking. So in this case, we could be thinking the whole circle here are moving, okay, when in fact they all are not moving. If you're interested, there's a link below. There's talk about how I explain to that. That has to do with the frequency of the device, of the pattern. So in terms of visual display here is very straightforward. I think you've seen most of this thing already. So like a direct view, so the image is really created in front of you. So in that case, start with this. I used this in my first lecture. So it's just a start with real image. So in the old days, we use this CRT cathode ray tube, which to have a laser, multiple color, and it could keep moving around using magnetic coil to kind of move them into a different location on the screen. Okay, and then people move on very quickly to a light emitting diode. So that one is LED. So you can see here with information. But nowadays, people start using them in everywhere. Okay. So the TV, LCD, OLED, so that's in place. So I think recently LG introducing transparent display. So that one is something could change the feel of some of the things that we do here. Okay, because that we're creating field of view in which you see through and then you see the objects like augmented reality. But generally the display are similar. Okay. Yeah. But other type of direct view display. Okay. So this one is like an iPad. Okay. Like a bendable display. Okay. So this one is, you can see there were some of them adapted into the phone. Okay. You see the Galaxy Note has a little curved edge that you can work with. and those kind of things. So there are quite a list of products that are available. Okay, so then you have electronic paper. Okay, so it was just like the Kindles, everything. The main difference with the electronic paper was designed to be easy to read to the eyes. So there's no active light source. Okay, so that means there's no backlight, or just like your normal computers, there's no backlight there. So that means it require a light source, just like real office paper books. You require a light for you to be able to read them. And then another thing is a projection display. Okay, so this one is we talk about a little bit here in the spatial display when you do tracking in space using projector. Okay, but this one is a bit big scale. So the HitLab, we have some of this system. Okay, so this is our older system. We have a new. This is on the back end. Okay, so right now we have a new system that's got a build of the television panels. Okay, so but this is a kind of projection system on the back. So you see the projector down here, and then there are three sides of that. So each one has two, which is one go to left eye, right eye, but you need to wear a glass, a special glass that has a filter on them. One different filter on one side, one eyes, and the other is a different polar system, uh, polarity. So that's creating a surreal graphic, just similar to concept to the movie theater in 3D. Okay, so in this case, the projection will go to reflect the mirror here, and then go back to the back of the screen, and then show up in the front here. So this is a real view projection. It's allowing you to walk closer without casting a shadow because projector is behind the screen. So this is a more expensive system, okay, cave system, cave automatic virtual environments. So this is a version where you use this usually as very expensive. So generally you are actually inside that system, and you can see projector everywhere. So they project on the back, on the side. So each one here, the person actually sit inside, normally like this. So you walk in. Sorry, you walk in, and then you have all wall boxing for you. So that means is that you will feel really inside the box there. Okay, although it's quite expensive. Okay, quite expensive there, especially when you look at the system that you actually have multiple core. This is at you see Urbana Champagne. So this is the whole system here. Okay, so you can see here it's bent around you sitting because now television panels much more cost effective and high resolution. So that means it's more and more popular here. We have a new system that we built 4 years ago. It's built based on similar technology, and you have seen the tractor on the top. Okay, so that's a tracking system. We will talk about that in the second half of today's lecture. So that's tracking your movement, tracking the controller, things like that. So and then this next thing here, I'll talk about that in the tangible user interface before. Okay. So in this case here, projection system is actually come from the bottom. Okay, so this is just a very creative way of building them at that time. So the image on the top here is building air hockey. So you should play it based on that. But instead of using air, they're just using the physical objects moving around. And then there has the light come from underneath. And that had been adopted into the people who actually use that to in the museum. Let's say you want them to do to digging in kind of find a dinosaur stone in the pattern there. So you just have them with the brush moving things around, and then underneath there's a camera looking at the special objects, whether we have a controller or something like that, and then it would actually interact as if it actually you are trying to clean something up on the table. So which is quite an intuitive way to do it. And this one is one of my colleagues working on the large dome front view. So this one is a project for a company called Kodak. Okay. At that time, we invest heavily in this kind of view. So basically, you're sitting on the dome. The projector is from the back. Okay, so projecting to the back of the dome here, and you are looking inside the dome. The position in which you sit is that your peripheral view will be just above with the dome here because it allows you to go slightly inside the dome. Okay, so that means that you will have a full view immersive. The tricky part for this one is geometry corrections, because the image, just like spatial AR that we talked about last time, is that when you project into the wall or the planar surface, this one is actually spherical surface, so that you have to correct geometry from the projection point of view. So the image, when it look from your end, it look proportionally correct. Okay, so we have that example in previous slide, previous lecture. Okay. And we have some.
Yeah, we can hear you now.
Oh, okay. No wonder why I keep saying. All right, so let me backtrack. Since I played a video. Okay. So was I here? Is this where I lost it?
Yeah, yeah, it was the
Okay.
projection loss.
Yep. All right. So I'll restart then. Okay. All right. So basically, I'm not sure how much you heard it last time. Okay. So in this case here, it basically you're looking at oh, I think I'm wrong video. Sorry again. Yes. So let me just not play with the video then. So this is the idea here is they have a wire on the headset. Okay, so the headset here has a projector. Okay, so a projector here has a neutral display. Okay, that actually you're going to be able to see it. Let me try to get to the space. So that's the image that you would see. Okay, from the video. Okay, so this is an image that you see that allow. The idea here is that a headset need to have a projector projected onto the surface, but the surface need to be a neutral color. Let me try to get to the part of the video that will show you that. Yeah, sorry, you can't hear it. Okay, this is probably the best thing. So this is there's no external projector. Okay, it uses a pico projector that attached to the headset. Okay, and you can see the little trick there. It's a retroreflective surface. That's where the projector required to use it, so that it actually doesn't go to any surface on the wall. Okay, you have to put this one in front of you. So, and all the interactive area, the one that you will see, the visual component will come from reflecting that. As I said before, the retroreflective materials are used in a lot of spatial AR because they require they give you a better control of the light. So when you put the projector light, or this in case this head mounted projector, the light go there and then basically come back. It doesn't reflect off to anywhere else, and that's what the unique property of retroreflective materials. Okay. However, that happened to be a bit of their limitation, because then the whole space here really need to be prepped for that. Okay. So hopefully that you get a sense of how the different people are trying in the past, try to get there, the dome display and different area. Okay. But now the current technology, okay, which is really most adopted in the industry now, is a HMD, the head-mounted display. Okay, so you will see different size here. You see Oculus Rift, you will see the Gear VR. So if you haven't seen it before, this is an older version, older generation of VR headset. So this one has a headset and has it has a cell phone that you can actually pop inside the headset. Okay. But this is now no longer industry standard. So it used to be when the VR kicked off in around maybe 6-7 years ago. And then you have go into a different form. Sony is the one that it's the only one that adopting this directly, not only in PlayStation platform, okay, not in Xbox. Okay. Now we have HTC Vive and also team up together, so that's another headset, which is the competitor to the Oculus. Okay. So the AR display itself is a HoloLens. Okay, so this is a HoloLens fully head-mounted display. So for those who come to practical session, you would have heard of this. Okay, so this will be a good one. But there are other previous version that people try, Google Glass in 2015, but that's not really AR technically AR system because it doesn't have ability to stabilize virtual object in space. It's simply just a head-up display, tiny prism right on the top right eye. Okay. And then you have Epson, which is a little bit more two eyes display. Projector come from the side, okay, of the display. It gives you a very nice view, okay. Not, however, it requires computer to run Android components. So it's probably good for certain work-related work, but it's not. Again, it doesn't really have like HoloLens, its ability to track its position itself in space. So therefore, it can render stabilized object in space. Okay, it just simply become a display. And that's a similar thing with Visip. Okay, so it's just a different form factor. So for that part, it's a control part. So now we are talking about we talked about the display part before the top here, and then now we're looking at how people will control them. Okay, so this one is going to be quite a bit of a long slide. Okay, so we'll try to see whether we'll cut them in half. Okay, so control input here, there were very different things. So for the rest of today's lecture, it's going to be various technology we are looking at. Okay, so you get a sense of that idea of what the technology could be. Some of which you're probably already using them. Okay, so the hand input here. Okay, so the hand input here, the reason I put them first because they're relatively quite getting more mature. Okay, so in this case here, they can have a different degree of freedoms. You can have a very different type, and how do you control them? So, okay, hand controller is not just about mimicking the hands. Sometimes you perform gestures. Okay, so that's what we call first displacement. Okay, so and how about secondary? How about the derivative of that, which is a third acceleration? So there are quite a few things. It's not just pointing the finger or touch objects, so it goes beyond that, depending on how you design them. Okay. So this is just a bit of historic figure. So this is just a typewriter in the old days. Okay. And then you move into mouse very quickly, and then you all various kind of controller. Some of these you have played them before. And there's an orb ball. So this is one generating the ball in the middle, so for you to grab and hold. And you can adjust a little bit of a displacement, but the key here is to be able to rotate it. Okay, so quite interesting one. Okay, so interesting example. So that's when we are pushing up. 20 years ago, there was a lot of this gear come around. So, and all this is called build for flight simulator. And for this one, is the game started to change 10 years later. The last 10 years with the interface, they become be able to touch them. So that's like Apples and all those screens that you are now familiar with, or phone and things like that. So that is a direct manipulation of the display. So, and before it used to be like this. So this is must date back for about 20 years. Okay, so the Palm Pilot. So that was before smartphone. Okay, it's a stylus base. Okay, it's a very just like the hand hold in the image on the left here. Okay, so the image is very small. So I mean, you can use a stylus. You can control. Most people use this for uh, control schedule control, and it's been popular in the late 90s. Okay, it's been popular there. It used to try to be the first to do the smartphone, but I think so Apple take it over, and then I think Palm Pilot goes sideways from there. And then we'll talk about these high space table before, the gesture companion, so that people can interact with it. And there's no, think about it, this is not a cast shadow. So there's no projector. If the project from the top, then you will see your own shadow. In this case, there's no shadow component. So there's a lot of same technology, but depending on how they design them. So this is one of the unique one. Okay. So the hand gesture itself, so this one is in the dome, if you remember earlier in the lecture. So in this case here, not just you see them in the dome space, but you also going to try to um, look at them and then perform gesture. In this case, I think it's funded by Ford company, the car manufacturer. Try to see whether what is the future car look like. This is like more than 20 years ago. So how people will interact, how people will able to control direction without steering wheel. Which surprisingly now, as with self-driving car, this kind of thing would kind of interesting to look at. Okay. So The image is a bit blurry, but essentially he's not just pointing there, but what he's doing here is he performing the gesture. Okay, and all this is just a bit basic informations like how he moved it. This is the view from the camera. Camera try using computer vision to determine the gesture based on the gestures the human performs. Okay. Of course, right now there's a lot of these feed into um, the deep learning. Okay, see if you know anything about machine learning. So in this case, is that before it used to be just computer vision part. It's like the kind look the foreground, looking for gesture structure. But in nowadays, start off by maybe 10 years ago by Connect version 1, all the gesture performed based on a million of training point sample. So in this case, only have 16. Actually, that's 18, 16 of that. So that means that it's very tiny. So, but right now, most of the gestures are performed based on the deep learning. So that means they're already pre-trained with 100 millions of points. So, and then the machines know precisely, even though you're not precisely perform the gesture, so they can guess pretty right there, pretty close. So that's a major advance in the past 5 years, again, driven by machine learning. So this one is actually has and this is very primitive here. You can see here the tree monitor connecting to the terrain, the virtual city. And then you can see here how he moved using his hand. The camera that looking at this is actually coming from the ceiling. What they learned from this one is actually it's relatively okay. Okay, it's not as robust as what we got today, but it's a foundation in which the today technologies are built. So, and then also there's old technology that people, it hasn't come back in this round of VR boom yet. This this data glove. So the idea was that this is all the fiber optics kind of run across here. So they will just measure the degree of bending between your finger. Okay, so in this case, you can tell how your hand is working. But nowadays, people will just bypass this one and then get to the machine learning approach, the hand gesture based on what they see. However, this graph here does bring hand actually add something that adds a tactile. Okay, so that means it could have vibration. It's not a force feedback. It's not one of those phantom things, the one that you can have mechanical arm that you can push against. This one is still a glove, but it's generate a sense of surface. You're touching virtual objects, so you may have a vibration that you generate. Okay, this is an object here. Okay. But it's still people. I think this is a relatively unknown area. Okay, not unknown, known, but it's underdeveloped. And there's some of things like this. Okay, the lead motion. So this is make a fraud many years ago. So let's just me forward to the. So you can see here. You can see here. So essentially here, what the device does is that let me try to get to the best image that you can see. Actually, this will be best. So the idea here is you see the hand and imitation of the hands on the 3D models. So the little joint is being detected. So the sensor was just underneath her hands. So that means that you're just waving. So what it does is that it emits some light. Okay, I have the sensor here we used in a previous project. So that has a light, and then I have a camera, two camera detecting how the light reflected off your hands. Okay, and then from that point on, it's not a machine learning, but there's a proprietary algorithm for the leaf motion here. Okay, so we use that project with my colleagues in chemistry to teach how to build chemistry. Okay, I think one of your project in 82 it has done to that, so that means great. So that means people can move the hydrogen, carbon, oxygen, and build them using their hand together as part of their tutorial for chemistry class. Okay. So Leap Motions, I think that right now they were struggling in the business, so now they try to repurpose some of their products for that. As I said before, right now the technology, machine learning start to come, and people now start to adopting that as rather than a specialized device. So this one is a project from one of my colleagues, also from back in the US. This one use electromagnetic signal sending out. Okay, similar concept to radar. Okay, so this one by Google Project Solid, but I think it's now in the products. I think it's run part of this in Google Pixel 4, which is how you interacting with the phone. So in this case here, it's actually you're not touching, you're performing, but you're not using the camera to look at your hands. They actually send a wave like a radar system in military, and then they're detecting how your hand is moving. And from the signal on the left here, you can see that's how they determine how your gestures are looking. Okay. So some of these projects is quite interesting. All right. I think let me check. I think this one is just about right. All right. Okay, let's do another few slide here, introduction. So for the rest of today's lecture here, so tracking controller. So this one is a relatively major technical issues, technical subject of the unit, but it's not really, you don't need to go to it, just have to understand a little bit of some of them. Okay. So why would tracking needed? Okay, I think we talked about this before. Okay, you might not know. From reading your 82, I noticed that some students don't quite understand what the tracking means, and then describe them in mixed modes. Don't really know what AR is, or things like that. So maybe this one I'll pay attention a little bit there. So what the tracking here is that this is a tracking could be applied to all field in our interface like VR, AR. Okay, but the example they use here is a more visual. Okay, so it's more attached to the AR component. So, but essentially here, ability for you to track your viewpoint in which you observe the view, either the VR view or the AR views. Okay, so you need to have ability to combine virtual and real world in the AR context. Okay, so for example, in this case is the image. Okay, so you have another virtual kind of sport red car there. Okay, so in order for you to put it there, you need to know where your cameras are looking, okay, where and that virtual contents is. Think about your euphoria, okay? Think about your astronaut as a card, and think about your virtual model where is it not by default it's sitting on your card or on the euphoria image, but you can manipulate them to other places. In this case here, as you can see, the red car is behind the building, okay, partially coming out of the building. So partially is included. So that's where I think Ron had shown you in the depth perception calculation of AR core. So that's precisely for this. But AR core, of course, AR core are not working from this distance. We're talking about more table or something in front of you. So that's allow you to see, okay, there's a physical object in front of you. In this case, it's a table, is this part of the building. So therefore, your virtual model from this viewpoint should be included. Okay. So, but having said that, is a registration here. If it's right now, you're in the world in which technology is relatively mature. There's not much many grid. There's not many competitive area. There's not much many falls. So there's quite a relatively almost industrial standard. Okay. However, if the registration is a problem, okay, so this is what is going to happen. Look like the image here. It has a little physical stick boom here, and the virtual plate is supposed to be attached to the top of this object. Okay. This is when this is captured from live image. So that means that the system has some problem, or it has some limitation, not a problem at that time. There was the latency in the system. So that means as these objects stick here and move around, you lose ability to be able to, you can see here, this is the latency here, that the mark is actually failed to keep up with the physical object. So that's what we call registration problem. Okay, so what that's going to mean here is that just like euphoria, your virtual object would not follow as either you have the virtual objects, the pattern of the euphoria, like the astronaut pattern there on the screen or on the card you print out, and you have the camera looking at, and you have just a visual virtual cube sitting on it. Registration problem will look like if you start to move the camera or you move the actual physical marker, okay, and then you start to see objects start not to be at the same location, not to appear to be drifting or lag behind or not at the same location. So it has a problem in it break the illusion. So you no longer just like if you think about it, 5-6 years ago when you play Pokemon Go, okay, which the tracking technology very primitive at that time. So you see the character kind of jumpy, not really appear to be on the ground. Like today technology, you should see that with AR Core, AR Kit. You should just see that on the surface, on the ground, on the surface, and things like that. It should look very, very much quite believable at this point. But that would happen then. So this is a really registration problem. Registration problem is actually has many component is not just it's a solve one thing. You have to make sure your display, first of all, your sensor need to be there, tracking need to be accurate, latency needs to be low, and the display need not to have a too large of optical, basically optical illusions components that you're not be able to map it into the display. It depends on how you use the display. So registration problem here is a very governance form. So everything that's wrong with your wrong with your AR or VR system, it will show up in the end as a registration. Yeah, for the VR part, registration will look slightly different. It would look like you're playing, but your scene is lacking. Okay, your scene is lacking. That could happen in the today technology if you bump in a lot. Like one of our current project that Ron is working with me is putting a lot of point cloud, which is millions, 30, 50 million points in there. So basically it's overloading the graphic card. So they're just having problem there. So that means that if your head is start, you want to experience the registration, you just keep moving your head as fast, very fast, rotate very quickly, change with it. You will see the scene was not really attaching, and very soon you'll get sick, motion sickness. That so you was because the whole scene would appear to be a latency. Anything closer to 1 second delay, I think you'd be in trouble for the VR. So that's the registration issues. Okay, okay. So in VR, which is it's the same problem that you're having, which is a tracking system and things like that, latency. So that was some area that used to be an exam question, but probably not this year. So like this, it's good registration, as I said before, is a governing term. So it's always require component inside it, accuracy, registration process, and latency, things like that to be correct. Okay. However, if you have accurate tracking system, you're not always going to be just like one component. It's not going to guarantee the whole big picture, which is registration, going to be accurate. So if you have, hopefully you get some basic understanding of that. So this is a typical coordinate system. Okay, you can see this in your Unity as well program. If you look at the objects, you will see as you're moving your camera in Vuforia, for example, you will see all this value in the profile to keep moving. Okay, essentially, it's a tree translation, which is X, Y, and Z, and tree orientation, pitch, roll, and yaw in that axis currently. So the reason this is a high common coordinate system, there's other coordinate system that people use, but in the Unity part is you use this mostly. You use this coordinate system, Cartesian coordinate system, which is a X, Y, Z, pitch, roll, and yaw. Okay, so this is the 6th degree of freedom here is a key. It's called full body rigid body movement. So that means you can define position and rotation of any object, rigid object, not liquid, not flexible, deformable object. Liquid object like solid object, you can define them in 3-dimensional space with this 6th degree of freedom coordinate system. So you have vector of 6, 3 orientation and 3 translation. And as I said before, if you're interested in this, you turn on your Vuforia, you will see this number moving as the cameras keep moving. Okay, looking at the Vuforia astronaut marker, you will see its numbers are moving, like based on how you move. And that's how if for a system for application that looking to modify and looking to technical distance, Those are kind of number that your program need to grab off. I mentioned some of these before. I just go through them a little bit in so head tracking factors. Okay, so there was accuracy. Okay, so how much it's accurate. Okay, so usually it's right now the tracking technologies are relatively for consumer use applications relatively within the ballpark. You can't tell the difference. Precision is minimum movements that can be measured. So this one is actually more precision systems. Accuracy and precision precision is think about is like a resolution. This is how best you do, but accuracy is usually a bit worse than the precision itself. Okay, unless you have a clever algorithms to kind of work out that one. Okay, so and then the next thing is update rate. Okay, so this one is very clear. So right now Oculus is running around 80 to 90 frames per second. Uh, HoloLens is a bit less, okay, 60 frame. Okay. But that's what it does is in the update rate is that it show you what's this system if the update is very slow. So what that means is that all the image that you're posing in the image will be slower, and not as slower. So you can really have the image that has a high dynamic scene movements in there. And then with the AR and VR area, the most component for update rate is not just the display; it's about your head rotation movement as well. Because think about it, you don't want to look at the slower movie frame rate inside the headset while your head is moving around. Yeah. And the fourth one here is a delay, which some people technically call latency. So that's we talked about that before. This usually is the one that caused the biggest problem. Okay, because other thing you probably once you build a headset, precision, pixel resolution, and tracking camera, refresh rate are built in. But the delay, so that means delay here could be latency of the system itself or the system that's running the VR. For example, if you run the Oculus or HTC Vive, and your system is running something else and your PC is running something else heavily loaded CPU and GPU, then it created latency. In that case, system is not able to update the frame rate, update the location of the system. So I mean the head tracking here, the position you track now might instead of available within 25 milliseconds, it's now become 50 or 100 milliseconds, which were closer to disaster then. So I mean, the whole thing would getting a bit slower, lag behind. So that's usually what most difficult to contain. Okay, and then of course the head tracking here. The last part was really about how you design them because right now people technology, as I said before, this one is more or less like a little bit of history because at this point, motion box is no longer that much of a deal now with the current technology. With using, we move to a slam base, which is a technology that you're using the camera to look at, and you combine with inertia, which we'll talk about in the second half of today's lecture. So in this case, before it was the tracking technology has limitations. So they're trying to know, okay, how much you're going to move. Are you sitting in, for example, most common is you're sitting in a fixed space like cockpit, pilot, or you're actually in the moving area in the lab. So those kind of things. How to track you from that? It require quite a bit of different tracking the technology to handle those. All right, so I think I'll take 10 minutes, okay, break, and then I'll stop the recording, and then I come back for this lecture, the rest of this lecture. Okay, so this is just talk about different technology. Okay, all right, okay.